to the fifth lecture. Yes, where we're going to be talking about something entirely new. So let's look at what we call an SCR. So this stands for silicon controlled rectifier, the silicon controlled rectifier. So what is its symbol? Its symbol goes something like this. It starts off like a regular diode, and goes like so. So this part is what we call the anode. This part is commonly denoted with letter A. This part is what we call the cathode, commonly denoted with letter K. So what this is, this is a PNP semiconductor device that allows the flow of electric current, in one direction only upon explicit triggering. So which brings us to the other part, which is the gate, commonly denoted as G. So this is nothing but a diode. So someone else could say this is a three terminal diode that only conducts in one direction only when a gate signal is applied, and it is a PNP device. So unlike our ordinary rectifier diode, that is made of a simple P and N substrate, right? So this is a two-layer device. An ordinary diode, right? So an ordinary diode has two regions, the P and the N. But for an SCR, this is a four-layer. It's a four-layer device with three terminals, control terminals, with one control terminal and two power terminals. So yes, 4-layer, and 3 junctions, 3 PN junctions, 3 PN junctions. So how would one look like? Let's try to visualize. So let's say the top part is our anode. It has P, N, P, N. So again, this is our cathode. So, and right around here, that's where we have the gate. So it is 1, 2, 3, 4 layers with junction 1 labeled as J1, PN junction 1, PN junction 2, PN junction 3, PN junction 3, right? So this is what we call a silicon controlled rectifier. So if we are to operate it, we will have to handle it a bit different from the way we handle a simple diode, simple ordinary diode. An ordinary diode. So this is the gate, that's the anode, and that's the cathode. So we are saying this is a device that lets current flow in one direction only, and that is the forward bias direction. The forward bias sense, that means this side is positive relative to the other side, right? It only lets that current flow through only when we apply a positive signal at the gate, a positive voltage at the gate with reference to the cathode, a positive with reference to the cathode. So current flows through the device. So this has serious applications. This has very, very useful applications. So we will look at towards the end of the lecture. So let's look at the conduction modes of such a device. So onto the conduction modes. So conduction modes on induction modes of an SCR. Conduction modes of an SCR. So the other name for the SCR is what we have as a thyristor. That's the other name, a thyristor. So the first conduction mode, that is what we call forward. This is what we call the forward blocking mode. We have a second one, forward forward conduction, mode, and we have the reverse blocking mode. So let's first look at the forward blocking mode. In the forward blocking mode, the thyristor or the SCR is forward biased. That's true. That's very nice. It's forward biased. But here it's forward biased. But the signal at the gate, let me call it VG, is equal to 0 volts. It's equal to 0 volts. So no gate signal is applied. No gate signal is applied. That is scenario 1. Scenario 2, VG is applied, but IG is not sufficient to turn on the SCR. So a thyristor completely depends on the gate current, which is partially controlled by the gate voltage. So the gate current is very important. So a thyristor or an SCR will fall into conduction mode if we have sufficient gate current, or we have adjusted the gate voltage just enough to have sufficient gate current. Okay, so what is happening to the diode in this state, whereby, in short, the IG gate current is just insufficient for any reason, whether the voltage has not been applied, there is no voltage at the gate, or the voltage has been applied but the gate current flowing through gate cathode, this gate cathode loop, right, is not getting enough current, right, to turn on the device for the main current. Let me just call it IL, current to the load, whereby that is not sufficient for the IL to start flowing. So remember, okay, let me just redraw it quick. No, let's do it like this. So let's utilize the diagram. In this condition, in forward blocking mode, this is forward by the device is forward biased. That's nice. But let's look at the different PN junctions. The first PN junction, junction 1, J1, in that case is forward biased. Now, but J2 is reverse. How this works is, imagine, so Imagine we have placed this positive. The moment we do that, no matter what happens the other side, it simply means positive to positive, that. So the first junction is going to be forward biased. But if we maintain this and imagine this is not there at all, so this positive would be as if we have a positive here, right? So that means this positive is going to go to the negative, to the end side of this PN junction. So this is reverse biased, right? Yeah. So that's why we have J2 reverse biased. If you use the same analogy, the same setup for J3, we'll find out that J3 is forward biased. So J3 is forward biased. So what will happen to the whole SCR? Since not all of them are forward biased, one of them is reverse biased, the SCR will be off. It will not allow the load current to flow. That is in the forward blocking mode. All right. So that is if the IG is small, very, very small, lower than a threshold value we are yet to cover just in a bit. So that is how the forward blocking mode operates. So let's look at the forward conduction mode. So these are the two conditions you need for the SCR to go from the off state right onto the on, into the on state, right? So long story short, a minimum gate current IG, the gate triggering current, must be subjected to the gate cathode loop such that the load current, the anode cathode current, or the load current in that case is sufficient enough to be above what we call the holding current. What we call the holding current, IH. Holding current, IH. This is the minimum load current or anode cathode current that is just required to maintain the SCR in the on state, even when the gate current is zero or the gate signal is turned off. You get the point. So that's what we call the holding current. We trigger the gate with a certain gate triggering current. The minimum required current to maintain the SCR in the on state, even when VG now is zero or IG is equal to zero. That's what we call the holding current. It is typically in the range of 5 to 50 milliamps for a couple of thyristors or SCRs. So what happens is that once the SCR is full on state, it will not go off even if we turn off VG, even if we set VG, the gate voltage or signal, to 0 volts, the moment, so long as IL, the load current, the current that's flowing through the anode and cathode, is greater than IH, the holding current, the device does not go off. It does not go back. No, it does not go back to the off state. So that's very important. That is one other difference we have with an ordinary diode. So it will stay on, not until that current goes way below the holding current. Again, then the device goes back to the off state. So that is how an SCR works in short. That is one way. There are very many ways of turning it on. There is another way whereby we apply a very large voltage between anode and cathode without even using the gate to turn it on. But we have to do that very fast. That is possible for very fast rising voltages. So that is, we will look at triggering methods. We will look at how we can trigger. We will look at how we trigger an SCR more in details later on. So in principle, that is the forward blocking mode. So the gate is just not enough to trigger the device into from off state to on state or into full on conduction mode where the anode cathode current is greater than the holding current. So that is when the device is waiting for the right conditions. Yes, it has been forward biased, but the turn on conditions have not been met yet. Okay, so let's head over to the second mode. Let's head over to the second forward conduction mode. So for forward conduction mode, this is what we have. So for forward conduction mode, I've cluttered the board a bit. So let me clear the board so that we can proceed. The forward conduction mode. We are on to another mode. What are the conditions for the forward conduction mode? So still we have to be in forward bias mode. That is one. Now let's just focus on the gate current. IG must be greater or equal to the gate triggering current. So we must have a gate current that is just enough. Remember, in the forward blocking mode, we had this forward biased, reverse biased, then forward biased. We need that current just enough to change this from a reverse bias to a forward bias. The moment we have IG sufficient enough to trigger. You get the point? So, and the load current IL must be greater than IH, the holding current. Must be greater than IH, the holding current. So, that's only when the thyristor or SCR transitions from the off state to the on state. So it's now a fully turned on switch. This is equivalent to a fully turned on switch. So a fully turned on switch. So that is the condition. We just have to forward bias. So in this case, we have junction 1, J1 is forward biased. J2 is now also forward biased. We have J3. It's no different. It's also forward biased. We have these conditions happening. We can have the thyristor go from full forward blocking mode to full forward conduction mode. So That's interesting. The other mode, let's continue with the last mode, that is the reverse blocking mode. What goes on in this mode? So first and foremost, the device now is reverse biased. The SCR is reverse. Here the SCR is reverse biased for starters. What's happening? So even if we apply a gate current, it won't matter, because what we'll end up with will be J1 junction 1, PN junction 1 is reverse biased, junction 2, J2, so J2 is, hold on, so let's first, to make sense, let's first go with junction 3. Junction 3, obviously that one is junction 3 is reverse biased. So junction J2, imagine this would be here, right? And this will be here. So this would come here and this will be applied here. So the junction 2 will be forward biased. J2 will be forward biased. So remember, only one condition leads to the SCR going from off to on. That is, if all of the three junctions, junction 1, junction 2, and junction 3, are forward biased. Only this. Only that condition is what helps the device transition from that state to that. And in reverse blocking mode, only a small, very small reverse, what we call a reverse leakage current flows through the device, so minute that it has zero effect on the overall current flowing through the load. So let's represent what we've discussed for now on an IV characteristic graph. All right, so before we go to the static characteristics, IV characteristics of an SCR, let's recap on something I discussed way at the beginning of the course unit. So in the very first lectures. So let's look at a scenario. Let's say we have a load, a resistive load like so. So we have a resistive load and we happen to be having a switch right around there. Let's say right around here we have a current measuring device. It's going to be giving us current values, all right, in amps. So we have a switch, let's call it S, and we have a voltage measuring device right around there, and we have power source, right? Like a battery of a certain EMF E, right? So let's say we have scenario 1, S is open. In short, the load is in off state, right? The load is in the off state. So if the switch is open, what are we going to get from the voltmeter? So we are going to get E volts because the switch is open. So the resistance of the switch is infinity ohms. Infinity ohms. And the current I flowing when the switch is open is 0 amps. So here we'll see 0 amps. So that is scenario 1. So here we're seeing I is equal to 0 amps. V is equal to E volts. And R is equal to infinity ohms. So let's go for the next. Let's first look at the second scenario when S is closed now. Fully closed. So it's a closed switch, right? So the load is on. Load is on. The load is on. So in that scenario, amps are no longer equal to 0. There is a certain current flowing through it. There is a certain current flowing through the switch, and that is equal to IL. The current measuring device is giving us some amperage. I'm calling it IL amps. But now the resistance across the switch, resistance RS, let me call it RS. RS is equal to 0 ohms. 0 ohms, right? Then the voltage drop across the switch is equal to 0 volts. So the switch is no longer dropping and it has no voltage drop across it, right? Exactly. So these are the important things to remember when we are to look at IV characteristics of static characteristics of any kind of switch. In this case, we have the SCR. We have the SCR IV characteristics. So the SCR in this case is the switch. So let's imagine, let's say we have positive voltage source going to a resistive load RL, and we are to use a thyristor. We are to use a thyristor. Or an SCR as our switch. So this is the one that's going to act as our switch. So let's say we are to measure the voltage drop across that resistance, that thyristor, and we are to measure. Let's say, let me extend this a little. And we are, let's operate the device in forward bias mode, right? Forward bias mode. So, and look at the current IL, or current through the anode cathode current, or load current through the thyristor versus the voltage. So, and we get to plot this IV characteristic. Let's say we are to do it like so. Let's say we have we have let's say we have what we get as VS, the VS in volts on that axis. So this is what we have as, let's call this parameter IAK, current through the anode and cathode. IAK, that's the positive part of the axis, that's the negative IAK axis, right? So that's the origin. So this is the negative VS in volts, right? All right. So with VG equal to 0 volts, what are we yet to have? So let's say we increase, let me call this VPP, right? The supply voltage. Let's say if we are to increase VPP, start it from 0 and we increase it, and look at what's happening to the current IAK, right? Current through the thyristor, so which is on this axis. We will experience a small forward leakage current, a very small, in the order of microamps, very, very small. Let's say we keep on increasing the voltage, it will be equivalent. Remember, in this mode, here the thyristor is in the forward blocking mode. So that means the whole supply voltage is still going to appear. The whole supply voltage is going to appear across, like we had in the first case, the whole supply voltage E appeared across the voltage measuring device. So in this case, we are going to have it open, so almost no current. So almost no current is going to flow up to a certain point, where the current is now almost increasing. Now it's starting to increase. So let's label that as VBO. So VBO stands for the forward break over. The forward breakover voltage. We call that the forward breakover voltage. Okay? So this is a voltage beyond which, if we increase VPP further and further and further, right, without applying any gate signal. So it's like we are testing how far can we go with the thyristor to a point whereby it is now transitioning from forward blocking mode to forward conduction mode. So how far can we push it without the help of the gate signal? So remember, the moment it conducts, the voltage across a switch, voltage drop gets to zero. The voltage drop across it gets close to zero. So, and the current spikes at the same, almost at the same time. And the current that starts flowing at that point, so the voltage drops. The voltage drops from a very large value, VBO, to a very small value close to 0 volts, like close to an ideal switch. So this is what we have as the ideal switch. I remember discussing this in the very first lectures. So this is what we call IH, holding current. IH, what I discussed in the previous few minutes. So this is what we call IH. So this is what we call the holding current. It is the minimum current below which the device will go from forward conduction mode back to forward blocking mode, whereby the thyristor or the SCR is off again. So if we are to make sure the device stays on, we must not go below the holding current. We will look at ways of forcing the current, mark the word forcing the current, the load current, IAK, forcing IAK. How do we force IAK to go below the holding current? In short, to turn off the device, to go back to forward blocking mode. So, and just above it is, slightly above it is IL, what we call this is IL. This is what we call the latching current. This is the amount of current required that flows through the anode and cathode, the IAK, that's required to maintain the SCR in full forward conduction mode, even with the gate current turned off. It is not that it's not that much bigger than the holding current, though the relationship between these two, IL is greater, slightly greater than IH. So if we were to look at typical thyristors and go to their data sheets, we will find that one of the given parameters of that specific thyristor or SCR is the latching current and the holding current. So this is always bigger than the other. So this region is what what represents the forward conduction. Let's call it forward. Let me write it around here. what we call the forward conduction mode. The device conducts almost instantaneously because it's now a switch. That means it will let as much current as is needed. So now let's change the setup a bit. Let's reverse. Let us reverse the circuit a bit. Take that point to ground. Negative. So let the cathode be positive relative to the anode. So this is VPP. Let's reverse bias the circuit, right? Okay. Still with RVG equal to 0 volts. So when we look at the IAK, it's a negative and very small value, very negative and small value that flows if we keep on increasing VPP, like we said, from 0 volts all the way if we keep on increasing the supply voltage. So we'll keep on seeing almost no change in the current, though in the reverse sense, because we've reversed the polarity, right, of the whole supply voltage VPP. Okay. So this is what we call the reverse leakage current, right? But this device has limits as well, like any other device. Every switch has limits. So if we keep increasing that voltage, we will reach a point. Let's call that one VBR. All right, I'm running out of space, so let me write here. VBR is what we will denote as the reverse breakdown voltage. This is the voltage beyond which if we keep increasing the voltage, right? That means increasing the voltage drop across the SCR, we will see an instantaneous rapid rise in the current, though in the reverse direction. So this is where the device breaks. This is where the device breaks and conducts in reverse as well. So when we are to select, we'll look at these things later on. When we are to select an SCR or a thyristor for a given application, we must watch out for the reverse supply voltage. Does it exceed the limits of the switch or it does not exceed? In forward, does it exceed the limits or it does not? Is the load current greater than the maximum current IAK the thyristor or SCR can handle, or is it within a handleable range, a range that is suitable for the device? So the IV characteristics of that thyristor can give you that information. So that's it for the IV characteristics. Let's just list in the last section, let's just list a couple of applications of such a device. Angle. So we will look at what the firing angle is. We will look at details on how an SCR switches. So that is in the triggering circuits, or what we call commutation circuits. We will look at that. What comes out of that? We have things like light dimmers, AC light dimmers. We have motor speed control, like the universal motor speed control systems, common in blenders, juice blenders, both domestic and industrial. We have light dimmers. I said light dimmers, heating, right? So heater control. That's where we will find such applications. So battery charging, by manipulating voltage current, we can charge batteries. So guys, that is in, remember I mentioned this way at the beginning. I remember that is in the PV industry, the solar industry. So charge controllers and battery chargers, that's it. Uninterruptible power supplies, UPS. We have batteries, we have to still to charge, we have to invert. Controlled rectifiers, very important in motor drives. So guys, an SCR is used in controlled rectifiers. So far we've covered uncontrolled rectifiers from our previous from our previous encounters with electronics, right? Our previous course units. So we will look at controlled ones. So we have what we call solid state relay designing. So instead of having electromechanical relays that create a lot of noise, arcing and parting, contacts welding shut, we use what we call solid state relays. They are made out of thyristors, tracks, and other devices. Electric welding machines. We have seen, I'm quite sure we have seen one electric portable welding machine somewhere. Trust me, there are thyristors on the inside. All right. So we have, because they have the ability to handle huge amounts of power rather than an ordinary diode. So we have, we can also have over voltage protection circuits. Imagine a circuit whereby the gate of a thyristor is connected to some saline voltage, some supply voltage. The moment it changes beyond a certain value, it triggers a mechanism through a thyristor. So that will be a very useful contraption or circuit. So induction heating. So guys, if we own induction cookers at home, or we know that in a metal processing factory, we have to melt down metals, heavy metals, serious heavy metals, thick, dense metals. So one of the methods we use, rather than getting a piece of steel and throwing it in a saucepan, we use induction heating, whereby we switch voltage and current rapidly, too fast, through a coil, and inserting a piece of metal inside manipulates or harvests, actually it harvests or utilizes the eddy current effect, thereby heating the metal to thousands and thousands of degrees Celsius, or hundreds and hundreds of Kelvins. So that is achieved by controlled switching through thyristors. All right. So soft starters. So let's say we are starting a motor, guys. Power electronics and machines, AC and DC machines, go hand in hand. So let's say we are starting a motor, a machine. One of the things you will learn, or you are yet to learn, is that the starting conditions of a motor or a machine is in a way that the starting current, let's say if it was a motor, the starting current is 4 to 5 times or even greater than that, the nominal rated current. So in order to avoid such issues, inrush currents and straining the power grid, we use soft starters. We control the turn-on voltage slowly. We ramp it up slowly. So a CR or a thyristor could help you. In transport, HVDC systems, high voltage DC systems used in electric trains. So how do we convert high voltage AC to high voltage DC? So we have thyristors for that in electric train systems. So that is just a tiny list of the enormous applications of SCRs. So let's end this lecture here. In the next lecture, we will be looking at the 2 transistor model of an SCR. Thank you.